co-host also.
Sure, sir.
Thank
you, sir.
Thank you to you.
Shall we start, ma'am?
Monica, please start.
Okay. So, welcome all of you on the second day of our STTP Advances in Civil Engineering. I, Monica Shah, will welcome you all for your valuable presence over here. Today, our speaker for the event is Dr. Saloni Pandya, Assistant Professor, Navrashna University, Vadodara. She has completed her PhD in Geotechnical Engineering from IIT Gandhinagar, Gujarat, and she has completed her bachelor's in Civil Engineering from LD Engineering College of Ahmedabad, Gujarat. Her area of research will be mainly in the unsaturated soil mechanics, cyclic instability of soil and the liquefaction susceptibility, soil dynamics, cyclic dynamic behavior of soil under the earthquake conditions, machine vibrations, and traffic loading. The ground improvement techniques, mechanical characterization of soils, soil water chemistry, and issues of problematic soils. She has a very vast experience for the research in the IIT Gandhinagar as a research fellowship from 2013 to December 2017. After that, she has joined the senior research fellowship over there in 2018 till she gets the postdoctorate fellowship in Technical University of Munich, Germany from September 2018 to 2000 through November 2018. After that, she has joined Namrashna University and she is presently working over here as an assistant professor. Her contributions towards the society will be having a very huge. She has published several papers in known conferences and journals, national as well as international. She has received a number of awards. The main will be the National Fellowship of Doctoral Students Award by the Ministry of Human Resources and Development. She holds the scholarship for the GATE qualification early in the doctoral studies. She has even received the Excellence Presenter Award in the Symbiosis on Earthquake Engineering, University of Shanghai, China. She has received many Best Paper awards and many other contributions towards the society. It is our pleasure to have you over here, ma'am. Now, I am inviting you for your enriched talk. Over to you, Saloni, ma'am.
Thank you, Monica ma'am, for such a generous introduction. Good afternoon to all of you and welcome to day 2. As Monica ma'am already specified, today's topic for STTP is dynamic behavior of saturated and unsaturated cohesive soils. So I hope the presentation is visible to everyone and I am audible fine to everyone.
Yes, ma'am.
Yes, ma'am, go ahead.
All right, fine. So soil, as compared to other building material, has a very unique and different characteristics, due to which the founder of soil mechanics or geotechnical engineering, Dr. Carl von Terzaghi, named it to be a very complex material since it is naturally made and not man-made. So what is that present in the soil that makes it so much complex? So first is it's a natural building material, so of course it is heterogeneous. No two soils in this world are ever same. They have different grain size distribution properties, they have different densities, different climatic conditions, different ways in which they have originated. The second and the most important is it has memory. In technical terms, it is known as stress history. So actually, if a certain type of load has ever occurred in the soil, its mechanical behavior changes according to that particular maximum load that has ever been subjected to it. The third property is it's a three-phase material. That is, it consists of individual solid soil particles, the air phase in the voids, in the pores, and the water phase in the voids and the pores. So there is a multi-phase interaction that is taking place simultaneously, and it changes with respect to the climatic and the geographical conditions. The fourth is it can settle. The settlement in the soil can go on for many years, as long as even 200 years. It has a plastic response. So there is a very small range of strains and stresses between which the soil remains under elastic state. 90% of the time, and for almost all the loads that is experienced by the soil in nature, it remains under nonlinear response, that is under the plastic state, and undergoes hefty plastic deformations. Finally, and the most important one is it has a transient response. So its properties, whether it is strength and stiffness, whether it is permeability, its compressibility, its settlement, changes with respect to change in the water content, change in the seasonal variations, in the microclimatic conditions, that is the drainage properties, etc. Due to which the soil wholesome is always classified as a very complex material which you cannot predict. However, it is not very difficult to understand it. So soils, like any other structural component, is subjected to basic two types of loads. That is, one is the static and the another one is dynamic. Statics, everyone knows that the loads does not change with time, it remains constant, right? And the static loads that the soil experiences are the ones from the superstructure, that is the dead loads, live loads, wind loads, the usuals. And the another one that is there is the self weight of the soil, that is the overburden pressure its own weight, which increases with increase in the depth of the soil. The final one are the dynamic loads, the one that changes with time, the one which repeats itself, right? So soil in nature are subjected to variety of dynamic loads. The first one, which makes to the top of the list, is the earthquake loading. So this is what the earthquake loading looks like, right? This is the acceleration time history of one of the earthquake. And you can see that it repeats, it is continuous, it does not have the same amplitude all the time, but it is short-lived. That means its duration is maximum to maximum 1 minute, which has been recorded till now, right? And that too, if it arrives for 1 minute, creates a lot of destruction. The second one in the series, and by the way, the earthquake loading can be considered as a dynamic or impact kind of loading, but it continues for a certain portion of time. The second one is the blast loading. So here there is a huge amplitude that takes place over here, the larger amount of amplitude, and then it repeats itself and ultimately it dies out with respect to time. It is short-lived as compared to that of earthquake. However, there could be after shocks that would result from the blast loading, and they are very frequent as compared to that of earthquake loading. Then comes the oceanic wave storms. So oceanic waves, they are repetitive loading. They come every day. They change with respect to the time of the day. They change with respect to the seasonal variation. They change with respect to the geographical locations as well. Right. Apart from that of the tsunami type loading, which again comes into the category of the earthquake loading conditions. Right. The machine vibrations, they are vibratory type of loading. They are repeated over several hours. So from 8 to 12 hours, they're continuously applied on the place where they're placed, right? On the foundation where they are placed. And the final one is the traffic or the railway loading, which is also a cyclic loading. And however, the amplitude of these three loadings, that is the traffic, railway, machine vibrations, and the oceanic wave, apart from that of the tsunami, are very, very less as compared to earthquake and blast loading. The frequency, however, is quite high. So these are the various forms of the dynamic loading. So what does this dynamic loading does to the soil structure? The dynamic type of loading causes localized pockets of shear deformations inside the entire soil mass. So there are pockets of shear deformations that takes place in the entire soil mass, which results into rapid permanent deformations. So if the same soil is subjected to static loading and the permanent deformations are going to take place after, let us say, certain hours, that will the dynamic loading will come to that situation quite rapidly. This would definitely lead to the stiffness degradation, and that too also very rapidly, resulting into the sudden failure of the soil mass. And that is the reason that the dynamic loading characteristics of the soils are absolutely imperative to evaluate. We are very much familiar with the static loading conditions and the static responses of the soil. However, the dynamic behavior and the dynamic response of the soil are still remains unexplored, and hence it makes us to the top of the research areas today. We are very much familiar with the monotonic shear strength properties of the soil, that is angle of internal friction and the cohesion intercept, which are very frequently used in the evaluation of the allowable safe bearing capacity of the soil, safety and the stability of the soil masses, of the slopes, retaining walls, etc. When the dynamic loading are subjected to soil, what we get from that are the dynamic properties. And which are those dynamic properties? They are shear modulus and the damping ratio. Right? This both are used for soil structure interaction application. They are used in the design of pile foundations, piledraft foundations, anywhere where soil and structure interacts with each other. They are used to model the soil properties. They are used to place itself in the constitutive relationships which are used to model the soil properties or to model soil as springs in the dynamic analysis. They are used in the design of embankments, retaining walls, simple as well as reinforced, and the design of machine foundations. So let us study what these dynamic properties are and how can we evaluate them. So before we study, let's just revise what are the components of the cyclic and the dynamic loading. I'm sure every one of you will be knowing this well enough, but we do have students with us and it's always good to revise it once. So the upper portion of any cyclic loading, so this is a typical S-shaped curve, as you can see, this is crest, this is trough, right? The amount of the force on the either side is known as the amplitude, right? The cycle starts from here, it goes down to here, and it completes here. So this is the definition of the first cycle. And the time required for the one cycle to complete is known as period. Frequency is defined as 1 upon period. So I'm sure all of you know this. I'm not going to spend much time on this further. So how do we apply the dynamic and the cyclic loading in the experimental forms? That means if I'm going to conduct an experiment to find out the dynamic properties of the soil, in which particular forms will I apply such kind of cyclic and dynamic loading? Let's go ahead and see them. So there are two forms by which I can experimentally apply cyclic loading on the soil specimen. The first one is the strain controlled one, and the second one is the stress controlled one. Now, they are very much similar to the definitions of stress controlled and strain control that we see in the monotonic loading conditions or the static loading conditions. So what happens in the case when I'm applying a strain controlled dynamic loading on my soil specimen? So the input is a strain value which is constant and repeated over a certain portion of time or repeated over a certain cycles, right? So you can see here epsilon is our strain and we are going to apply this particular constant value of strain for a certain number of cycles on the soil specimen. Now, when you apply strain, the stresses are induced within the sample, right? And these stresses are resisted by the specimen. So the output that we obtain when we apply strain are in the form of stresses. So if the strain is applied in the axial direction, the stresses that we are going to obtain are the axial stresses or the deviatoric stresses as they are commonly and technically known as. So here we can see that due to the applied dynamic loading in form of strain, initially the resistance of the specimen was very high since there was no degradation that the soil specimen has experienced ever, right? Now with time, with increase in the number of cycles and increase in the time of the dynamic loading, we can see that there are localized deformations that are formed inside the specimen, as a result of which the resistance of the soil decreases and a time comes when the stress or the resisted stress by the specimen reduces to zero. So at that point of time, we say that the specimen has absolutely failed, right? So this is what we input and this is what we get as an output in the case of the strain controlled dynamic loading. Now, if I plot this deviatoric stress that we have obtained as a part of output and the axial strain that I have given as a part of input, we are able to obtain this beautiful stress strain response, which in technical terms is known as the hysteresis response. It indicates the plastic deformation that is occurring and the permanent deformations that is occurring in the specimen. So if you clearly and very carefully observe, initially the stress that was resisted by the specimen was very much higher for the same axial strain amplitude that you had applied, right? And therefore, the first cycle has the biggest loop. As the resistance decreased, the size of the loop decreased, indicating the reduction in the stiffness of the specimen, as well as reduction in the strength carrying capacity of the specimen. Let us now go to see the stress-controlled dynamic loading. So as the name suggests, we are going to control the stress. That means we are going to apply stress over here. So my input quantity now is the stress here, a certain quantity of stress, let us say 4 kg, 6 kg, which gets repeated over a period of time and a number of cycles. Excuse me for a moment. I'm very sorry for the interruption. Yes, let's move ahead. Yeah. So as already explained, in the case of the stress controlled condition, we are going to control the stress. I'm going to apply a very constant value of stress, which gets repeated over a period of time or a number of cycles. So in that particular case, I will get axial strain as the input, because if you apply stress to the specimen, there are strains that are induced or developed inside the specimen, which basically leads or takes the particular material to the failure, right? So initially, as you can see, there is no change in the value of axial strain. So the sample was very, very effectively able to resist the applied stress that we had given. After around 10th cycle, there is an increase in the axial strain that has taken place. And after that, the axial strain has exponentially and wonderfully increased, right? So you can very well see that there is an absolute and a sudden change in the axial strain that takes place. And when the axial strain reaches a value of 5% in the positive compression side and 5% in the negative compression side, a specimen is said to have reached the failure conditions. Right? Now, when I draw a hysteresis response for such a stress control dynamic loading condition, I can see over here that initially, when there was no change in the strain value, there was absolutely no change in the size of the hysteresis loop. Now, when the axial strain had tremendously increased, you can see there is a tremendous change and increase in the hysteresis loop. And a point has reached when we reach 5% of axial strain in both positive and negative directions, we have reached the failure conditions. Okay, so depending upon the type of analysis that one wants to carry out, we can select the stress controlled and the strain controlled loading conditions. The strain controlled are highly preferred because whenever any devastation takes place, we cannot know what and how much magnitude of stress or load created that particular devastation. But we can know how much displacement in the soil took place. We can know how much deformation took place. And that is how we can back calculate the amount of the strain that it would have experienced. And based on that, we can conduct the strain controlled dynamic loading very effectively. Okay, so basically by using this hysteresis response, whether you have conducted the stress controlled testing or we have conducted the strain control testing, using the hysteresis response, we can obtain this GND, that is the shear modulus, and the damping ratio, the dynamic shear strength properties of the soil. Right? So consider this is a typical hysteresis loop that I have drawn over here for a single cycle, one cycle itself. On the x-axis, you have axial strain, and on the y-axis, you have the deviatoric stress or the axial stress, the cyclic one. Now, if the loading, the cyclic loading, as in this particular case, is applied in the axial manner on the specimen, then from this particular graph, I cannot directly obtain the value of shear modulus. I have to use the elastic properties, which you have already learned as a part of your solid mechanics, right? And by evaluating E, that is the Young's modulus for a particular loop, and using Poisson's ratio information, I can calculate the shear modulus of the soil. Now, E can be very easily obtained by connecting a line between the two extremities at the positive and the negative side passing through the origin and getting the slope of this particular line, we will be able to obtain the value of the Young's modulus. As far as Poisson's ratio is concerned, Poisson's ratio for exosymmetric condition and for saturated soil masses can be obtained as 0.5 irrespective of the type of the soil we are dealing with, because it depends upon the boundary conditions and the saturation condition of the soil mass. If the soil mass is saturated, irrespective of the type of the soil you have, the value of the Poisson's ratio will always be 0.5. However, if we are dealing with unsaturated condition, then we have to obtain the Poisson's ratio of that particular soil specimen for which you want to obtain the dynamic properties. So you have to obtain it either using unconfined compression test apparatus or by using the consolidated drain testing information. You can obtain the V, that is the Poisson's ratio for unsaturated specimen. Right? Okay, in the similar manner, damping ratio, which indicates the amount of the energy that is dissipated by soil mass. Now, any material from which the waves passes, any kind of waves that are shock waves, seismic waves, any kind of waves that passes, can dissipate energy by undergoing deformations. So we already saw that whenever any soil is subjected to dynamic loading, it undergoes deformation, and that is how it actually reduces its stiffness. And when the deformation takes place inside the soil mass, it dissipates energy. And the amount of dissipation of energy can be very easily articulated by obtaining the damping ratio of the soil. It is also obtained from the hysteresis loop by dividing the area of the loop, right? And the area of the triangle that is formed. So the two triangles that you're able to see over here is OAB and OCD. If the symmetry is maintained in the compression as well as the extension side of the loading, then you can consider only one triangle's area and can place it here. This particular equation is only for one triangular area because the 2 times of the triangular area has already been taken care of here in the 4 figure that has been placed here, right? So by this simple formulation, you can very easily obtain the value of G and D. Now the area of the loop can be obtained by using the trapezoidal rule or the Simpson's rule, whichever is convenient to you. The smaller the sizes of the sections, the more accuracy will be there in the evaluation of the damping ratio of the soil. Okay, moving forward to the types of G, that is the shear modulus that are used as a part of the design parameters in variety of situations. So there is something known as G max. There is something known as G-sec, that is the shear modulus or the second shear modulus. This is the maximum shear modulus. And there is something known as G10, that is the tangential shear modulus. Gmax is the maximum shear modulus that you can obtain for the soil mass when it is subjected to extremely less strain applications. That means if I have applied a very less strain controlled loading, that is the magnitude of the strain that I've applied, the amplitude of the strain that I've applied is very less, then the sample, the soil specimen will still be in the elastic range, and the amount of the shear modulus that you will obtain for that elastic range is termed as the maximum shear modulus. As already discussed earlier, the elastic range of soil is very less. If the strains of the order of 10 raised to minus 6% to 10 raised to minus 4% are applied on the soil, only in that particular range, the soil remains in the elastic nature. Anything above that, the soil quickly turns into the elastoplastic state and then finally the plastic stage, right? So if I want to obtain Gmax, I have to apply extremely small amplitude of strains on the soil while applying dynamic loading, and will be able to obtain Gmax from the first cycle of loading. G seconds incorporates, or the second shear modulus incorporates, the plastic nature and the nonlinear characteristics of the soils. It captures that very, very well. And it can be obtained by joining the line from the center of the backbone to the extremities of the backbone, and then obtaining the slope of this particular line. The tangential modulus is not very much used as far as the design considerations are concerned. However, one can obtain for the research satisfaction, I would say, and that can be obtained by simply drawing a tangent line to the hysteresis loop and then obtaining the slope of that line. So G and D are to be obtained for each cycle of loading. If you have 100 cycles of loading, we are supposed to obtain it for 100 cycles of loading. So there will be 100 values of G's and 100 values of damping ratios, to be precise. Okay, so which particular test can give me the value of maximum shear modulus, and which particular test will give us the value of second shear modulus? So low strain amplitude test and high strain amplitude test are two types of dynamic tests that could be performed on any soil specimen. The low strain and high frequency amplitude test will simulate any kind of vibratory loading conditions such as machine foundations, and to a certain extent some portion of you can say the traffic loading and the wave loading condition, but up to a certain extent only. Here the frequency range is very high, ranging from 10 Hz to 200 Hz. However, the amplitudes of the strain applied are extremely low, that is in the range of 10 raised to minus 6 to 10 raised to minus 4, in order to ensure that the specimen always remains under the elastic range. The two tests which can help to obtain or apply such kind of loading conditions on the soil specimen are the resonant column test and the Bender element test. This is a typical setup of a resonant column test. The black portion that you can see here is the soil specimen. So a cylindrical hollow soil specimen is prepared for this test at the density and the water content at which you want to obtain the dynamic properties of the soil. And then it is subjected to the torsion strain over here at the top. And the bottom portion is fixed. So a vibratory type of loading is initiated from the top to the bottom, and the hysteresis response is obtained. Using that hysteresis response, we can obtain the value of Gmax for the first ever cycle of loading, right? Similarly, this is the Bender element setup. You can see these two pieces are known as Bender elements. They contain a very small chip at the top as well as at the bottom. They are placed at the top and the bottom of the cylindrical soil specimen, as you can see here. Their function is to transmit the shear wave throughout the soil specimen. So they first transmit it and the other one receives it. And the time lag between the transmitted and the received signals is calculated, which in turn will give you the shear wave velocity that was passed through the specimen. And using a simple relationship between the density and the shear wave velocity, we can obtain the Gmax, that is the maximum shear modulus of the specimen. Now, since by using this Bender element test, you can actually ensure that there is absolutely no axial strain that is developing inside the specimen. So whatever small axial strain that is developing is very, very less, and the sample remains completely under the elastic range. As a result of which, the results from the Bender element test are considered to be quite lot accurate in evaluation of the maximum shear modulus of the specimen. Coming to the evaluation of the second shear modulus, which incorporates the nonlinear nature of the soil. And for that, we have to perform high strain amplitude and low frequency testing on the soil specimen. Now, there are two tests which can help you achieve this. The first one is the cyclic triaxial test, and the second one is the cyclic simple shear test. The high strain amplitude and the low frequency loading can simulate very well earthquake and blast loading conditions, which have extremely high amplitude, but they occur for a very, very short period of time, right? And that is how they can very much simulate this behavior well enough. Okay, so this is the cyclic triaxial setup. It consists of a cylinder. You can see a load cell, which can help you to measure the resistance of the soil to the applied axial strain loading. An LVDT, which is known as the linear variable displacement transducer. It's a sensor which can help you to know the deformations that are taking place inside the soil specimen. Right, the pressure panel, which can help to apply the corresponding confining pressures and help you in evaluation of the pore water pressure. A control box to which all these sensors are connected, and the hydraulic actuator, which will ultimately help you to apply the cyclic or the dynamic loading on the specimen. Right, and however, here the cyclic loading is applied in the axial manner. That means in the axial direction, the cyclic loading is applied. So here first we will have to evaluate the value of E, and then only we can obtain the value of G. In the case of cyclic simple shear setup, the size of the sample is very less. And here the loading is applied absolutely in the form of the shear force or the shear strain. So the hysteresis response that you receive from this particular test will be between the cyclic shear stress and the shear strain. So you don't need to evaluate the value of G directly by from the slope. You will be able to obtain the value of the shear modulus directly, right? So these are the different tests which can help us to evaluate the value of G max and second shear modulus experimentally by incorporating the dynamic loading on the specimen. Okay, so what are the range of frequency for the dynamic of cyclic loading that will help us to simulate a certain type of loading on the soil specimen? So let us say if I want to simulate earthquake type of loading conditions, then how much should be the frequency that I should choose, right? So you can see the earthquake lies somewhere here. It's a combination of wave and vibrational loading together. However, it has a very high amplitude. You can see the time of loading is somewhere between 1 minute to 0.01 minute, right? So anything in this range you can select. The number of the cycles, that maximum number of cycles that can simulate earthquake loading conditions are around 50. Right, so in the similar manner, you can see the various other natural loading if you want to simulate that using the SAID apparatus that I had just described, right? The blast loading, traffic loads, machine foundation, wave-induced loading, etc. And these are the range of strain amplitude that can be applied, which will tell you that whether the soil will remain under elastic state, elastoplastic state, or it will be near to the failure range. So that will help you to decide the amount or magnitude of the strain that you need to apply cyclically in order to obtain the dynamic properties of the soil. So after this will be kind of concluding the introduction to the dynamic loads and the corresponding dynamic properties, how to obtain them with this particular slide here. So there are two forms of cyclic loading in which you can apply the SAID axial strain amplitude or the cyclic stress on the soil specimen. The one is the two-way loading. Now, two-way loading means if you incorporate two-way axial strain amplitude on the soil specimen, it will first initially compress the specimen, then it will bring it up to the neutral position, and then it will pull or extend the soil specimen. So basically, it will apply compression loading, then it will come to the neutral form, and then it will apply the extension loading on the soil specimen. That is why it is known as two-way loading. The upper one is known as the one-way loading, and here the soil specimen or the object does not go into the extension phase. So there will be no pulling of the soil specimen. So you just load it, you compress it, load it, and then you unload it. So there will be loading and unloading. The earthquake loading conditions or the blast loading conditions will follow the two-way type of loading, since the particles will go in compression to the neutral base and then in extension. Whereas the traffic loading or the wave loading will simulate one-way loading conditions, because there the traffics or the waves are just going to compress and then unload itself. So they're going to just load and unload itself. So depending upon which particular type of loading you want to simulate and for which loading you want to obtain the dynamic properties, you can choose from the various cases. Okay, so with that, let's start with the dynamic response of saturated cohesive soil. This particular portion is a very small portion of my PhD research work. And the reason that I have selected cohesive soil has something to do with the environmental concern. Now, for maximum all the infrastructure projects or civil engineering projects, the type of soil that is chosen are always cohesionless soils. The one which does not have the cohesion component, the attraction between the two similar forces or the stickiness in them. So the type of soils are all types of sandy soils, gravelly soils, silty sands. They are all your cohesionless soils. The basic reason why they choose cohesionless soils is because they are very easy to work with. They do not require any expertise labor. They're very easy to compact. They have excellent drainage properties. They are highly permeable. They have wonderful strength characteristics. However, the concern with respect to environmentalists is that that particular resource is getting depleted day by day due to construction of various structures, its use in cement industries, concrete industries, etc. That is the reason the researchers are forced to concentrate on the cohesive soil as research, because this will initiate the use of locally available soil for the construction of soil structures. They are very much interested to use locally available soil in the construction of the soil structures. And for that, if they have to modify the soil, if they have to improve the soil, that is okay. But for that, they want to know the properties of the soil, how they behave under certain loading conditions, whether they are able to sustain that loading, whether the pore water pressures develop in them are not so much high, etc., etc. The problem with cohesive soils are that they are very difficult to compact, and the magnitude of the pore water pressures that develop in the saturated conditions are a concern. And that is the reason they are difficult to work with. But in order to improve them also, or to use them with a certain modification or a factor of safety, we have to know the parameters of this soil. And that is why the concern or the researchers are now diverted towards their evaluation of the properties for the cohesive soils. So let me just discuss first the saturated portion, and then we shall go to the unsaturated portion and how they are different. Okay, so the soil under consideration was taken from Ahmedabad, and these are the various geotechnical properties of that soil. In this particular phase, we will understand how to interpret certain behavior of the soil and why such behavior actually takes place. Okay, so the soil was predominantly a fine-grained soil because it has a very much higher portion of silt and clay. The clay is 32%. So it will not be wrong for me to say that the entire mechanical behavior of the soil, that is the strength and the compressibility characteristics of the soil, are governed by the fine-grained characteristics or the fine-grained material in the soil. Okay, the liquid limit that the soil had possessed is 51% and PI is 31, that is plasticity index, which also indicates that all the mechanical characteristics are governed by the particular clay proportion in the soil. The soil was classified as CH, that is the clay of extremely high compressibility and plasticity. The various other parameters are obtained for its in situ conditions. So as I already discussed earlier, cohesive soils have very less permeability. So what happens is when we try to saturate the specimen in the similar manner as we try to do for the cohesionless soils, that is sands, it will take days, even months to saturate the specimen. And that is a very time consuming job. So in order to avoid that, we make saturated specimens. And how can we do that? We can do that by using the slurry consolidation technique. And this is the slurry consolidometer, which was used for the present study. So let me just introduce you to the different parts of it and what does it do. So its action or its working is very much similar to the conventional consolidation test that we perform in the geotechnical engineering lab, right? However, instead of the soil mass, here the soil slurry gets consolidated. So you can see over here, a soil slurry is prepared by taking a certain portion of dry soil mass and then adding a water content equivalent to that of 2 times the liquid limit of the soil specimen. The soil slurry is prepared. It is left overnight or for 24 hours so that the proper cohesion gets developed between the soil specimen. And since it is clay, there are chances of the specimen to expand a little bit. So whatever expansion has to occur will occur during that particular time of 24 hours. Once it is left and proper bonding is achieved, it is poured in this perspex cylinder. Now, the perspex cylinder has 2 drainage holes, one at the top, at the bottom. Here there would be a filter paper and a porous stone that would be placed, which will allow the drainage to occur from both the sides in the upward direction as well as in the downward direction. At the bottom plate also, you will place a porous stone and a filter paper to allow only the water particles to pass and not the soil particles. The slurry with the assembly is then placed here in the slurry consolidometer, as you can see over here. And then with the help of piston, they're connected to the pneumatic cylinders. Right? With the help of pneumatic cylinders, pressures are applied and the consolidation begins. So it takes around 2 to 3 days for the soil cake, saturated soil cake to develop. Now, depending upon the type of density you want to achieve, you will select the amount of pressure. So if the pressure of, let us say, 50 kPa is selected to be applied on the slurry, then the resulting soil cake will have lesser density and higher water content. And if at all the pressure that you select to apply is, let us say, 200 kPa, then the resulting soil cake will have more density and lesser water content. However, both the specimens will be 100% saturated. Right? The extracted soil cake that you can see after end of 3 days was obtained like this, and its dimensions were 100 mm in diameter and 200 mm in height. Out of which the soil specimen to be placed in the cyclic triaxial equipment was having the dimensions of 50 mm and 100 mm, which is extracted from it and placed. But first time when we use such kind of study consolidation technique to obtain a soil cake of a certain density, it is important to check the water content distribution since it's a huge sample. So how can we do that? We cut this soil cake into number of pieces and then we obtain the water content of all those pieces. The variation in the water content should be less than plus or minus 2% in order to ensure that the uniformity is obtained, and the specimen has densified at all the points in the similar manner and has same water content. After obtaining the soil cake, the sample is extracted using the soil extraction equipment, and then it is placed here in the cyclic triaxial setup. Once the sample is placed, there are 4 particular stages that the sample is subjected to. The first stage is the assembly. In which we place the specimen on the lower platen, which contains a porous stone and a filter paper. The sample is placed. Then again at the top we place a filter paper and a porous stone, and then a latex membrane is placed on its covering. Let me just show you that in detail. Yeah, so one more moment. Yeah. So this is what the sample looks like after you have assembled it. There is a filter paper here, a porous stone here. And then in order to ensure that the water is passing very nicely and uniformly throughout the entire specimen, we placed radial filter paper strips. That is the vertical filter paper strips, which will help you in the radial drainage, which will again reduce your time for the consolidation. Once it is placed, the cell is filled with water. You can see the cell. It is filled with water. Then the water flushing is carried out, in which the water is passed through the sample and then taken out of the sample in order to create a proper water path throughout the sample. Once it is achieved, you force saturate it. So the sample is already saturated, but we need to ensure that the entire assembly is also saturated. And as a result, we apply back pressure. So again, from a particular hole that is present inside this lower plate, the water is forced inside and a force saturation is achieved. Once the force saturation takes place, you consolidate the specimen at a certain confining pressure. So confining pressure is applied with the help of the water that is filled in the cell. You apply corresponding to the depth at which you want to obtain the dynamic properties of the soil. So if I apply 50 kPa confining pressure, the amount of consolidation will be less. If I apply 200 kPa confining pressure, the amount of consolidation will be high. Depending upon at which particular depth you want to obtain the dynamic properties of the soil, you can choose the corresponding confining pressure. Okay, so once the confining pressure is applied, the drainage valve is open and you allow the water to drain outside. So there is a decrease in the density of the specimen, and the time for the consolidation usually takes place around 14 to 17 hours. And with the help of filter paper strips, they are actually reduced to this many hours, or it can go to 24 hours or more also, depending upon the type of the cohesive soil that you are dealing with. For my case, it was 12 to 14 hours. Okay. And then comes after the consolidation is complete, when there is no further change in the dimension of the specimen, there is no further drainage of the water that is taking place. We stop the consolidation and then we shear it. So when we are shearing it, now is the time when we apply the axial cyclic load on the specimen. So the type of testing that I had done was strain controlled two-way loading on the specimen. So actually the strain in the cyclic particular fashion was applied on the soil specimen as a whole. For a certain number of cycles, and for a certain frequency and amplitude. So this is what the system looks like, and with the help of LVDT, you will be able to record the constant strain that you have applied, and with the help of the load cell, you'll be able to obtain the load resistance that is developed by the soil due to the application of the cyclic strain on it. Okay, so each test to complete will take around 7 to 8 days. And this were the 2 series that were performed in order to see or in order to evaluate the dynamic properties of the soil. Okay, in the first series, we had seen the effect of frequency. So 4 particular samples were prepared and they were tested at different frequencies. However, the axial strain amplitude was kept constant. The frequency variation was from 0.05 Hertz to 1 Hertz, and the amplitude range from that was kept constant for the series, that is 1%. In the second series, that is series T3, 3 particular samples were tested at a constant frequency, and the amplitude was varied from 0.6% to 1.5%. Now, these samples were subjected to the simulation of the earthquake loading conditions. They were subjected to 100 cycles of loading, and the confining pressure maintained throughout the test was 100 kPa. The dynamic parameters, that is the G and D, were obtained at this many cycles. So at the 0th cycle, that is the first cycle, then up till 4th cycle, then 10, 20, 30, because there was a certain portion which remained constant. So then they were evaluated at the variation of the 10 cycles. And then finally, at the end, they were evaluated at 20 cycles. That is 60, 80, and 100 cycles, as you can see from the figure here. So this is a typical cyclic loading that you can see that was applied on the specimen. You can see the strain remains constant at 1%, right? And this is the corresponding output in the form of load that we have applied. We can convert that to stress and we can obtain the hysteresis response. So this is a typical one. I had obtained similar curves for all the types of samples that were tested, right? So first we will talk about the influence of the frequency on the dynamic characteristics and the dynamic properties of soil. So let's just see that. Okay, so A1 represents the specimen that was subjected to the lowest frequency, and A4 represents the specimen that was subjected to the highest frequency. Right, here it shows the hysteresis loop response. If we very closely observe, now this is how we interpret any kind of dynamic response that you obtain. So if we very closely observe over here, we can see that as there is an increase in the frequency of loading, the inclination of the hysteresis loop, that is its rotation with respect to the horizontal axis, increases. Right? Which indicates that with increase in the frequency of loading, the stiffness of the soil specimen increased, the strength of the soil specimen increased. Let us see over here the pore water pressure response. I'm sure every one of you knows what is pore water pressure. However, for the students who are present here, I would just like to specify what it actually means. Now, whenever any kind of load is applied on a saturated soil mass, that load is resisted by the water that is present in the voids, right? And that particular pressure or the resistance pressure that is offered by the water is known as the pore water pressure. We can obtain that during the shearing stage when the drainage valve will be closed and the pore water pressure is evaluated using the pore pressure transducer that is attached over here. So what happens when we apply the loading of different frequencies, right? So you can see that as the frequency increases from A1 to A4, the pore water pressure that has developed also decreases. RU over here is the ratio of the pore water pressure that is developed during the shearing stage to the confining pressure that we have applied on the soil specimen by the water from the sides, right? Now, when, if at all, the RU value reaches 100%, then we say that the soil has completely lost the strength it was having and the soil has liquefied. So this is what is the major difference between the dynamic properties of cohesion-less soils and the cohesive soils. In the case of cohesion-less soils, after certain number of cycles, it won't ever reach 100 cycles. After certain number of cycles, let us say 20 or 30, depending upon the density of the specimen, this RU value will reach 100. Whenever this reaches 100, the pore water pressure becomes equal to the confining pressure. The effective stress, which governs the strength of the soil, reduces to 0, and the specimen is said to have liquefied. Right? So for cohesive soils, there is a beautiful component of C that is present in the soil, that is the cohesion that is present. It tends to hold the particles together. So even if the effective stress reduces to 0, the sample will never ever liquefy. Of course, its strength reduces. However, there will be not at all a condition where there will be 0 strength, right? And that is what is being specified over here as well. So if you have a very low frequency, you are able to reach the RU value is 75%. So you can say that around 75% of the strength of the soil has degraded. Now, as the frequency of the loading increases, this RU value is decreasing, which also indicates the same thing, that the stiffness of the specimen is increasing and the strength of the specimen is also increasing. Going ahead, looking at the dynamic properties, that is the shear modulus and the damping ratio for the specimen subjected to different frequencies, we were able to understand that the specimen which is subjected to the highest frequency has the highest shear modulus as well as the damping ratio, right? And the one which was subjected to the lowest frequency has a lesser shear modulus and a lesser damping ratio, right? There is another parameter which is very, very important to evaluate if you are evaluating the dynamic parameters of the soil, which is known as the cyclic degradation index. It is the ratio of the shear modulus for the nth cycle to the shear modulus of the first cycle. It tells you the amount, magnitude, the quantity, how much stiffness degradation has taken place with increase in the number of cycles. You can see, let us consider the specimen A4. So for A4, if you see that with increase in the number of cycle, there is a progressive decrease in the shear modulus of the specimen. Amount or how much degradation has taken place can be obtained from this particular parameter over here. However, if you compare it with different frequencies, there is no particular trend that came out for the specimen having different frequencies. So irrespective of the type of the frequency the specimen was subjected to, the amount of stiffness degradation that took place in them was nearly very much same, right? The lower the value of delta, the higher is the amount of the stiffness degradation that has taken place in the soil specimen. So one thing that we were able to understand from this is that if we increase the frequency of loading, the strength, stiffness, that is the shear modulus of the specimen, the damping characteristics of the specimen increases. However, the pore water pressure reduces significantly. This is because the frequency of loading means the rate at which a particular strain is applied to the specimen. How fast is the strain applied to the specimen? Now, faster is the loading, that is, the higher is the frequency, the lesser time will be available for the cohesive soils to develop a certain amount of pore water pressure in them, since their permeabilities are very less. Now, lesser is the amount of the pore water pressure that has generated, the lesser will be the internal localized deformations that would be occurring in the soil mass. As a result of which, lesser are the deformations, the higher will be the stiffness and the strength of the soil. However, a large or higher number of frequency results into development of localized shear zones in the specimen. And that development of shear zones helps in the dissipation of the energy that is being supplied to it, helps in the dissipation of the cyclic loading that has been supplied to it. And that dissipation can be very, very easily evaluated from the damping ratio. That is why for the specimen having a higher frequency, we were able to obtain a higher damping ratio. Now let us see what happens when we increase the axial strain amplitude. So here is the hysteresis response of the specimen subjected to the various axial strain amplitude. C1 here indicates the specimen which is subjected to the lowest amplitude, and C3 is the highest amplitude that is present here. So with increase in the amplitude, the size of the loop increased, right? And the inclination decreased. Similarly, the pore water pressure ratio was found to be more for the specimen subjected to the higher amplitude, indicating a higher deformation, larger localized deformations inside the soil specimen, as a result of which we can see the decrease in the strength and the stiffness of the specimen subjected to higher amplitudes. Let us see the G and the D responses. The G response, or rather I would say the values of shear modulus, was found to be maximum for the specimen subjected to the lowest amplitude, which makes sense. The smaller is the amplitude, the larger would be the strength of the soil. And as the axial strain amplitude reduces, the stiffness also reduces significantly, more than 2 times. The damping ratio, the damping ratio was found to be higher for the specimen subjected to a higher amplitude, which makes sense. So if the amplitude is more, the localized shear zones that would be developed in the soil specimens will be more. There would be a larger dissipation of energy and hence higher damping ratio. The cyclic degradation index response also indicated the similar thing, that the specimen subjected to a higher axial strain amplitude underwent maximum stiffness degradation as compared to the specimen that was subjected to the lower axial strain amplitude. Okay. T is the parameter known as the cyclic degradation parameter, which helps you to know the rate of degradation of the stiffness, the velocity with which the stiffness degrades in the specimen, the speed with which the stiffness degrades. Right? It is the slope of the log delta versus log number of cycles curve, and by obtaining the slope of that particular curve, you will be able to obtain the value of T, and from this value also it was signified that the specimen with the highest amplitude had degraded faster, so the speed of degradation was faster. And in the case of amplitude, in the case of frequency, the specimen subjected to lower frequency, the speed of degradation was faster. Okay, with that, this is how we interpret the results of saturated cohesive soil specimens. Now let us go to the unsaturated cohesive soils. The major difference between the saturated response and the unsaturated response is that in the earlier one, that is in the saturated case, the specimen or the soil mass was only having 2 phases. The first one was the solid phase of the solid particles itself, and the second was the water phase, since all the voids in the soil were filled with water in that particular saturated specimen. Now, when we talk about unsaturated state, there is another third phase which is introduced in them, and that is the air phase. Now, when air and water mix with each other, they are 2 immiscible fluids, and they give rise to a very unique quantity which we are going to introduce in the further slides. So the soils which are having degree of saturation less than 100% possesses negative pore water pressures. The one which have completely 100% saturation, they are positive pore water pressures, and they will resist the load when the load is applied on it. Whenever the negative pore water pressures come into picture, it gives rise to a quantity known as suction. Since the air, which is also a type of a fluid, and water, they both mix with each other, they are immiscible fluids, resulting into the formation of the air-water interface, which helps in the development of something known as matrix suction. Now, this negative pore water pressures are present in many soils around the world, since around 33% of the world's surface area comprises of hyperarid, arid, and semi-arid regions. Now, in this particular regions, the Meadows zone layer, that is the unsaturated zone layer, extends up to very, very larger depths, 50 meters, 100 meters, 200 meters, etc. So there is a wide range of soil which remains under unsaturated state, right? Apart from the natural occurrence of this unsaturated soil, there are many other phases in which the unsaturated soils are found in the place. So let me take you to those phases first. So apart from the natural occurrence of the soil in the unsaturated state, there are many soil structures in which we use compacted soils, which are also under unsaturated conditions. The structures in which we use them are the retaining walls, tunnels, highway railway embankments, covers of waste contentment, pavements, airfills, earthen dams, natural slope linings. Everywhere we use compacted soils which are under unsaturated state. So what happens when the specimen is under unsaturated state is the development of this negative pore water pressure that we called as suction. Suction can be further divided into two types, that is metric and osmotic. Suction, as the name suggests, it's the attractive force of the soil for water since it is unsaturated. So it has affinity for water, it has attraction for water, and so it can pull the water from the place where it is abundant. And the only place where it is abundant on the ground is the water table. Right? So it is the force with which it can pull out the water from the place of abundance. There are two particular types, that is metric and osmotic. The metric suction arises due to the capillarity and the surface tension phenomena, basically due to the presence of air-water interface, the meniscus in the unsaturated soils. And the osmotic suction, which arises due to the change in the solute concentrations. So if the soil has any kind of salt content in it, only then the osmotic suction arises in that. Majorly, the entire mechanical behavior, that means the strength, stiffness, compressibility, permeability, all of this for unsaturated soils will be governed due to the presence of metric suction and will be governed only by the metric suction. Right? It governs the entire mechanical response of the soil in unsaturated state. So whatever principles of conventional soil mechanics that we were applying to saturated soils cannot be applied here in the case of unsaturated case. Mathematically, metric suction is the difference of pore air and the pore water pressure. So if pore air pressure, if we consider to be atmospheric, this will be 0 and will be left with the negative pore water pressure with respect to the water table that is present. Right? The presence of this suction terminates the implementation of principles of conventional soil mechanics to unsaturated soil mechanics. Many failures have taken place due to non-consideration of this metric suction in the strength and the stiffness characteristics of the soil, whether in the static loading conditions or in the dynamic loading conditions, such as earthen dam failure due to prolonged rainfall. We have seen it in many times that due to so much rainfall, there was a landslide that was happening. There is a earthen dam failure that is happening is because the metric suction values reduces fastly to 0 whenever the excessive rainfall occurs on them. The seasonal variation of the earth pressure on the retaining wall. So when we design the retaining wall, we have in mind that, okay, the earth pressure that we have calculated will not change but that is absolutely wrong. The transient nature of the soil plays this magic over here, that with seasonal variations, the temperature variations, the metric suction in the soil changes, as a result of which the strength and the stiffness of the soil changes. The change in the phreatic line, the change in the slope stability slip surfaces with respect to change in the environmental condition owing to the change in the metric suction of the soil, the unstable vertical excavation during the construction of the foundation where they have not considered the effect of metric suction into account. In expansive soils, metric suction plays a very important role. Due to the change in the metric suction, the cracks can develop and can hamper the structure in a very hefty manner. There is a possibility of cracking in the unsaturated soil zone that is being kept over here in the landfill area, where we do not want the effluents and the leachates to go to the water table. There is a soft soil layer that is placed here, and there is a cracking that takes place due to the change in the metric suction. And this is what can lead even in the GCL, that is geosynthetic clay liner. So basically, incorporation of metric suction in the strength and the stiffness characteristics of the dynamic characteristics of unsaturated soils is extremely important, and that's what we are actually going to do today. So let us discuss how the dynamic properties or the behavior of the soil is different under unsaturated state and the saturated state. So what was done in order to note the difference is that initially the specimen was loaded cyclically in the same manner in which we had loaded the saturated specimen. So the specimen will go in compression, will come to the neutral zone, and then will be taken up in the extension phase as well. What we got to know is that in compression phase is behaved exactly same as that would behave in the case of the saturated state. However, in the extension phase, there was an absolute linear response. There was no stiffness degradation that was observed. You can see over here the loop inclination is changing as the number of cycles are increasing. However, in this particular extension phase, we were able to see absolutely no stiffness degradation. This particular behavior is very much similar when you apply cyclic loading to any rubber specimen. So what was actually happening, and then on careful observation, we got to know that the specimen was compressing in the similar manner as the saturated specimen would compress. However, while the extension phase, only the latex membrane was actually getting pulled up. So if you see over here, the only latex membrane was getting pulled up. So it would compress exactly in the same manner as the saturated specimen would compress, but in the extension phase, only the latex membrane was getting pulled up. Latex membrane is made up of rubber, and that is what was happening, that is what was actually reflecting in the extension phase of the hysteresis loop response. Now, in order to overcome this, we applied an initial static axial strain. So initially, statically, monotonically, a certain percentage of strain was applied on the specimen. And then immediately cyclic loading was applied on it. Now this static initial load that we were applying, or static initial axial strain that we were applying, we ranged it from 0.2 to 2% to see how it behaves. So when the static initial axial strain was 0.2% and the cyclic axial strain was 0.2%, the S by C ratio, that is the static load to the cyclic load, was obtained as 1. As the initial static axial strain increased, this S by C ratio also increased. We had kept the cyclic axial strain constant at 0.2%. And then we did the cyclic loading on them at a frequency of 0.5 Hertz and a cell pressure or the confining pressure of 100 kPa. And the loading was continued for 50 cycles. Let's see what happens in the case of that response. Now we can see as the S by C ratio increases, that means when the S value, the initial static axial strain, increase, we could see over here that the extension phase performance of the soil specimen improved. So at S by C ratio 10, we could see the same kind of stiffness degradation happening in the unloading phase, or rather I would say the extension phase of the curve, similar to that of the compression phase of the curve. And hence this was taken as constant and was continued to be applied for the rest of the testing as a part of the next series. Now the question lies that what did this application of S equivalent to 2% did to this unsaturated soil specimen? So what was actually happening is that whenever the specimen is in unsaturated state, there is an air-water interface that develops, which gives rise to an internal compressive intergranular forces. So the effect of this intergranular compressive forces, it holds the particles together. It won't allow it to move in the extension zone. It will not allow the specimen to pull out. It will actually hold it very, very strongly. Due to which the specimen was not able to be monolithic with the loading piston. As a result, when we were applying the force in the extension zone, the specimen was not getting pulled up due to the presence of this intergranular compressive force arising due to the metric suction that is present in the soil. As a result, we were able to obtain absolutely no stiffness degradation in the unloading or the extension phase of the curve. Now, when we applied an initial static axial strain, shear deformation took place in the upper portion of the specimen sufficiently to allow plastic deformation to occur in the upper portion of the specimen so that it can become monolithic with the loading piston. Now, due to the application of this initial static axial strain, there was a densification that took place in the soil specimen, as a result of which there was a minor increment in the shear modulus of the specimen. However, the damping ratio up to S by C equals to 7.5 did not show much variation, but with S by C application of 10, there was an decrement in the damping ratio, indicating that yes, there was a shear deformation that took place in the initial portion, plastic deformation that took place in the initial portion to make the specimen monolithic with the loading piston. Moving forward. So after that, we have understood how to apply dynamic loading using the cyclic triaxial equipment on the unsaturated specimens. We had done a series of testing. And since we all know that metric suction governs the overall strength characteristics of the soil, it was also important to evaluate how much suction is present in the soil at a particular dry density and at a particular water content. So it was evaluated using the filter paper method. I will not go in detail. If you want to know more about unsaturated soil mechanics, we can keep another session for that. But it was evaluated using the filter paper method. The cyclic loading applied has had an axial strain amplitude of 0.2%, which was continued for 50 cycles. Frequency was kept at 0.5 Hertz, and the confining pressure or the cell pressure that was applied for all the series of tests were 100 kPa. And these are the results that we had obtained. The dry density and the water content selected for the sample preparation ranged in this three manner. 1.74 is the 100% maximum dry density, 1.64 is the 95% maximum dry density, and 1.46 is 84% maximum dry density. The variation of the water content is as follows, and the corresponding metric suction that we have obtained for different specimens at different dry densities and water content has been tabulated in this particular table. The G value and the D value presented here indicates the shear modulus, the average shear modulus and the average damping ratio for the first 5 cycles of loading. Now, if we pay attention over here to these results, at a particular dry density, the metric suction value was found to be maximum for the specimen that was prepared at the lowest water content. In the similar fashion, the shear modulus was also found to be high for the specimen subjected or prepared at the lower water content. The average damping ratio did not have much variation. However, if you see for the various number of cycles, we were able to see a nice trend in that as well that we will discuss when the figure comes out. Okay, so this is for a particular dry density. So that was same for all. For this also, it was obtained to be highest for 9.5 and the G value was also obtained to be highest for the lowest water content. Similar was the case with 1.74 gram per cc dry density. Now, at a particular water content, if you see, with increase in the dry density, the shear modulus was tend to increase. However, the damping ratio, the metric suction was found to decrease. Makes sense. When the dry density of the specimen increases, there is a closer packing of particles which incorporates a proper bonding and a proper intergranular friction, which will help increase the strength and the stiffness of the specimen, and that was visible from the results. However, the decrease in the metric suction with increase in the dry density was because as you increase the dry density, for the same water content, since we were talking about the same water content, 9.5% here, the degree of saturation for the specimen that is prepared at higher density increases since the void ratio decreases. So if the degree of saturation increases, the metric suction also decreases. Okay. So this was a major observation that we obtained from that. And similarly, the same observation we could also reflect from the hysteresis loop responses. So there were many hysteresis loop, but I have only included typical ones. So this for a particular dry density, you can see that with increase in the water content, the inclination of the hysteresis loop decreased, which indicates that as the water content increases for the same dry density, there is a severe loss in the strength and the stiffness of the soil. And at a particular water content, you can see that with increase in the dry density, the inclination of the loops increased, which indicates that the strength and the stiffness of the specimen increased with increase in the dry density. So these are the damping ratio parameters that we wanted to discuss. That for a particular dry density, you can see over here that the damping ratio was found to be minimum for the specimen subjected to the specimen prepared at the lowest water content. And for a particular water content, you can see that the damping ratio was found to be more for the specimen that was prepared at the higher dry density. So what happens in the case of why the damping ratio increased for the specimen that was subjected or prepared at a lower water content, in spite of it having a very high value of G, that is the damping rate, that is the shear modulus or the strength of the soil, right? So that answer specifically lies over here and can be explained by this particular schematic diagram, which explains the phenomena very, very well and in a very crisp and a nice manner. So in this condition, the figure A represents a pendular stage, that is when only the meniscus water is present. That means the soil contains very less amount of water. Right? What happens during that stage is when the water content is less, the metric suction of the specimen is very, very high. That we were already able to see from the test results over here. That means at the lowest water content, the metric suction is higher. Now, if the metric suction is higher, this Fe, that is the capillary force that is developed, which connects these two particles together, between which this meniscus is formed, will be extremely high. You can see the magnitude of the metric suction here. It is 7,781 kPa. So the capillary force that is developed at the lower water content is extremely high. Now, when this force is high, it results into the higher load carrying capacity of the soil specimen, as a result of which we were able to see the higher values of G for the specimen which has the lower water content. Right? Now, what happens when the water content increases? Now, as slowly the water content increases, the metric suction reduces. And this capillary force weakens. So there is a little bit separation among these two particles. On further increase of the water content, this separation increases owing to the further lessening of the metric suction. With again further increase, the particles move apart due to the further weakening of this. And at complete saturation, the particles are apart, the air-water interface has disappeared, and there is no capillary force that is now holding the soil particles together. Hence, when the water content increases, this capillary force reduces, which was actually helping the specimen to have a higher loading capacity, as a result of which there was a sudden decrease in the stiffness of the specimen. Similarly, due to the disappearance of the air-water interface or the disappearance of the metric suction with increase in the water content, there will be a higher localized deformations that would be occurring in the soil specimen, as a result of which we were able to obtain a lower value of damping ratio for the specimen that was prepared at higher density, because the closer packing of arrangement is still there for the specimens which has higher density. However, we could very easily identify one specific observation from this is that for a lower water content, the dissipation of energy is higher. So in spite of specimen having a very high value of metric suction, very high value of shear modulus, that is the stiffness of the specimen under dynamic loading conditions, the dissipation of energy is more for the specimens that are prepared at lower water content. Looks very strange. The dissipation should be less because the deformations should be less if you have higher strength and higher metric suction. The similar response was obtained when you see the cyclic degradation index. So this was for a particular dry density. I have shown here the variation of the cyclic degradation index. The lower values indicates more amount of stiffness degradation with number of loading cycles. So the higher stiffness degradation, a large stiffness degradation actually, was obtained for the specimens prepared at lower water content. And this observation was similar for all other densities as well. So basically, the specimen which was prepared at a lower water content, which possesses higher metric suction, which possesses higher stiffness, higher strength, degrades faster, degrades more, degrades heavily. So this is what the degradation can be very easily explained with the help of the schematics, that whenever a cyclic load is induced in that, there is a straining and rotation of the menisci that takes place due to the displacement and the rotation of particles, which ultimately reduces this particular capillary force that is present between the soil specimens in the unsaturated state, leading to larger localized deformations and hence higher damping ratio and a larger amount of stiffness degradation. Thus, to conclude from the study, we could say that the specimen which has higher metric suction has higher stiffness, of course, but higher initial stiffness, because the stiffness degradation with respect to number of loading cycles is also found to be more since the delta decreases. If delta decreases, the stiffness degradation is higher. So the specimen having lower water content, higher metric suction, unsaturated state has higher stiffness, but it crumbles faster. It loses strength faster. It loses stiffness extremely faster. So it shows fatigue resistance. It shows higher brittle response, lesser fatigue resistance. And this happens in spite of possessing higher stiffness and metric suction, which indicates that a soil mass under unsaturated state possesses a metastable structure, a metastable interparticle structure, which is highly vulnerable to the disintegration of the soil matrix. It has higher strength, but it crumbles faster upon wetting, that is increase in the water content, or upon loading, which indicates that this particular material is potentially unstable, fragile, and dangerous. So if at all any kind of dynamic of cyclic loading is subjected to the specimen under unsaturated conditions, that is to the specimen which has high suction or in high suction soils, it would lead to a rapid loss in the stability of the soil mass in spite of being unsaturated. So there is a specific misconception that people have that saturated conditions are considered to be the worst case scenario. No, it is not like that. Even if in the case of unsaturated state, the initial strength and stiffness is higher, but it loses its strength extremely faster. And the matrix of the soil is very vulnerable to disintegration, which actually poses more threat to the loss of the stability of the entire soil structure as compared to that of the saturated conditions. So with that, these are the other ongoing research areas. I'm involved in few of them. The dynamic properties of unsaturated soil under suction controlled cyclic loading. So you apply suction in that and then you apply cyclic loading. Then dynamic behavior of low plasticity cells. This area is also not very much explored. Properties of all problematic soils such as micaceous soil, soft marine clays, collapsible laterite soils, expansive soils, powdered boulder that is found usually in the Himalayan regions, and pure clays like kaolin. Now this particular type of soil or this particular response to the dynamic properties or its evaluation is required because kaolin is now used as a bone substitute for the people who have to, whose bone gets cracked and you have to replace it with a steel metal body. The research is going on in using kaolin as a bone substitute. So for that particular purpose, they want the properties of dynamic properties of kaolin in that. And the corresponding treatment to improve the behavior, then under a varying confining pressure. So usually in some traffic loading conditions, the confining pressure also varies. Not only the actual stress, the confining pressure also varies. With varying deviatoric stress, like in the actual earthquake loading conditions when the deviatoric stress varies with respect to time. And then incorporation of all the results that we have obtained into a constitutive model. So you can predict the soil mass or the soil behavior in a better manner. You can predict the soil model in a better manner for the dynamic analysis in the soil structure interaction. These are the various references. These three are my papers, which gives a very detailed information about what we have discussed today. If anyone wants to read, they can contact me individually. These two are the books from which I have taken references. This is my contact information. Thank you, everyone. I hope I didn't bore you all, and thank you very much for your patience. If there are any questions, you can ask them now.
Thank you so much, Saloni ma'am, for your enlightening lecture. I hope everyone got something with them after this and they will get some new research area for their own research work, right? Guys, now our forum is for open for the question answers. You may ask question answers to Saloni ma'am.
Yes, ma'am, I have a question.
Yes, please go ahead.
Yes, sir. Yes, ma'am. We have talked about the Poisson's ratio that we are using the formula of G might be. So for
Yes.
the unsaturated, for the saturation, you told that generally we are taking 0.5.
For saturated conditions, we are taking 0.5.
And for unsaturated condition, you said that we need to do the UCS
UC
test.
test. UCS, yes. So
Yes.
how can you obtain, you want to know how can you obtain the Poisson's ratio using UCS test?
Yes.
Yes, okay, I'll tell you that. Okay, so let me just take one more slide over here. I hope it is visible. So what
Yes.
have, it is visible? The slide is
Yes.
visible
Yes.
to all of you?
Yes, ma'am.
Yeah.
Yes, ma'am.
It's
Yeah,
blank. Yes.
okay. Yeah. So what happens in the UCS test is UCS is a simple compression loading without any confining pressure application, right? And that is why it is known as unconfined compression test. So we apply the strain from the downward direction. There is an upper fixed boundary, right? And the specimen is loaded in this particular fashion,
Excellent. Yes.
right? Actually. Now what happens if you put two dial gauges, two or three, if possible for you to keep three dial gauges, then keep three, it will give you a very accurate result. I had kept three while I was determining the Poisson's ratio for the unsaturated soil that I just showed you, right? So if you keep three dial gauges in the three directions, dial gauges can tell you the deformation in any direction it is placed, right? So if you place it literally, it will give you the deformations in the lateral direction. So with the help of lateral direction deformation, you can obtain the lateral strain. You already have the longitudinal strain, right?
Yes.
You can obtain the Poisson's ratio and
Okay.
obtain the maximum one at the failure. That will help,
Okay.
right? If you want to know about more, I can share you some details about that as well. Okay.
Okay. Also, and the last in the test dynamic properties, in the last that we have taken the some samples, we have compressed it at the MDD, then 94% of the MDD.
Yes, yes.
So it's a odd number. So it's any specific reason why we have taken 94 and 84?
Yes, I'll
Because
tell
it's
you
odd
that.
number. So I have
No, actually, I wanted to take at 95 because you know that in field we cannot ever achieve 100% MDD,
yes.
right? So even the code also allows us to keep it at 95%, right?
Yes.
Now, in certain retaining wall areas as well, when we want to ensure that the natural vegetation grows, right? So
Yes.
there are many places now that we want the natural vegetation to grow in order to avoid any kind of erosion. There we have to even compact it at a lesser density. So 84 to 85% is considered to be best for that scenario. And here also in this case, 94 to 95% is what you can actually achieve in the field. And that is why I had taken 94% since it was a whole number. 95, I was not able to obtain the whole number.
Okay. Thank
Okay. Yeah.
you.
Any other questions to other people? I guess there is no question.
Okay, if you have any
Yeah.
questions, you can directly contact me. My contact information is available on Navrashna University's website, as well as we will share this PPT, so there also the information is there. Thank you all for listening.
Thank you, ma'am.
Okay. Thank you so much, guys. Feedback link is going to be shared in the WhatsApp group as yesterday was sent, and please send the feedback.
Ma'am,
Before, yes.
ma'am, I am getting the link of the lectures.
Okay, I will do the needful. Don't worry.
Okay, thank you, ma'am.
Okay. Yeah. One more request to all of you before signing off. Can all we have keep our cameras on? So I'll take one group pictures for the STTP. All of you, please
That is a
keep your
good
camera.
idea.
Yeah. Please keep your cameras on. Okay, I'll take this picture at least. Okay. So we'll done for the day. We'll see you tomorrow at 2:30 p.m. Okay. Have a nice day. Goodbye, guys.
Good. Bye.
Hi, everyone.
Bye.
Thank you.
Bye, sir.
Thank you. Bye.